8.1 talks about general linear transformation. Chapter 8, we're going to take a slightly different direction. It's kind of what we've been doing, but now we're going to reset or redefine everything. We're going to focus on, well, a linear transformation from V to W is a map from the vector space V to the vector space W. Then if that's a mapping, then T is a linear transformation from V to W if the two properties hold. One, K is a constant or scalar. Oh, there it is. If K is a scalar, U and V are vectors. The transformation on KU is K times the transformation on U, and transformation of two vectors U plus V, where U and V are in V, is T of U plus T of V. So the additive property and homogeneous property hold. In the special case where V equal W, the linear transformation is called linear operator. Now we're going to define a few things. This is an alternative to this. So this is what we've been doing all along for a subspace, so to speak, the constant multiplier and the sum. Alternatively, if we have a transformation from V to W, and this is a linear transformation, then T of 0 is 0. T of the difference is the difference. And instead of K times, we use -1. You could do that as well. Now, redefining a few things. Let the transformation from V to W be linear for which the vector space V is finite dimensional. If S consists of the bases of V, then the image of V can be expressed as the transformation of V would be a linear combination of the bases, where C sub 1, C sub 2, C sub 3 are the coefficient required to express V as a linear combination, or the weights. Defining what a kernel is, let the transformation from V to W be linear. Then the set of vectors of V that T maps into 0 is called the kernel. So you want everything to map to the origin. That's called the kernel of T, denoted by kernel of T. The set of all vectors in W, remember you're going from V to W, are the image. So this is the pre-image, this is the image, this is like domain, and this is range. So the set of all vectors in W, which is the range, of at least one vector in V, because you could have multiple vectors pointing, that'll still be a function, i.e. linear transformation, of at least one vector of V is called the range of T, and we denote it by R of T. Now, just to know, if we have a linear transformation from V to W, then the kernel of T, the kernel of this transformation, is a subspace of V, and the range of T is a subspace of W. We're redefining the rank and nullity. Well, just like before, nothing different. Let T be a linear transformation from V to W. In the case that the range of T is a finite dimensional, its dimension is called the rank of T. And if the kernel of T is finitely dimensional, then its dimension is called the nullity of T. Kind of like, rank, null, and what was it? Rank, null, and dimension. The dimension would be the rank plus the null. So we're going to denote those by rank of T and null of T. Remember, the rank of T is the range. So it's really in W. Well, dimension theorem, let T be a linear transformation from V to W from a finite dimensional vector space V to a vector space W. The range of T is finite dimensional, and the rank of T plus the nullity of T equal the dimension of V. We did this before, we're going to play with it again. So kind of like saying V equal rank plus null. Suppose T is a mapping whose domain is the vector space M of 2, 2, something like this. In each part, determine whether T is a linear transformation, and if so, find the kernel. Okay, well, finding the kernel is not that bad. Just to make sure that the outcome is gonna be a 0. Well, here, the linear transformation focuses on A sub 1, 1, just that piece right there. Well, let's see. Determine if T is a linear transformation. Well, if I take the transformation of Ka, then that is Ka11. If I multiply this by K, that would be Ka11. I could say that's K times A sub 1, 1. Oh, which is K times the linear transformation of A. So the constant multiplier holds, and if I take two matrices A and B, then that's going to be, based on it, that's going to be A plus B 1, 1. Well, hey, so let me recall this. There we go. So this is going to be Ka. This is going to be A sub 1, 1 plus A sub. Oh my God. B sub 1, 1, which is so the addition holds as well. That works. This transformation maps everything to the 0. Right? That's a range. Well, if I take K and I apply it to it. Oh, I didn't find the kernel. I forgot about that. It says to find the kernel, right? Every time. Find its kernel. Well, all what you have to do is take the transformation on A, B, C, D. And that's going to be A. Set that equal to 0 in your set. So set just A sub 1, 1 equals 0. Every time you apply this transformation, it's going to map everything to 0. And that's all there is to it. So pretty much T consists of all of these vectors. If you use A sub, all of these matrices. Here, well, we already have the 2 by 2 being 0. Well, we know that if you take T applied on Ka, that is 0. You could say that's K times the 0 matrix, and that's K times T of A. So the constant multiplier holds, and if you take T applied on A plus B, that is 0 over 2 by 2 plus 0 over 2 by 2. That is T of A plus T of B. So there it is. And here I should say kernel of T. And here kernel of T is pretty much defined to be any of those will do. It's going to be mapped to 0, 0 anyways. So there's no restriction on them. You could choose them to be anything you want. And if we have this transformation given A, it just takes C, where C is a constant, and multiply it by A. Well, okay. if I apply the, oops, if I apply the scalar multiplication, T sub Ka, well, that's going to be C times Ka, yeah? So whatever it is, you multiply it by C, but I know from constants I could switch those, and isn't that key? T sub A. So, and if I take the transformation applied on A plus B, that would be C into A plus B. That would be CA plus CB, which is T of A plus T of B. Well, therefore, it holds. So T is a linear transformation. Now, the kernel here, well, we have two conditions. If C equals 0, then the kernel of T would be any of those. If not, if C does not equal 0, then the only way you could map everything to 0 is to force all the entries to be 0. Then when you apply the map on it, it's going to take everything to 0, 0, 0. Now, determine whether the map T is a linear transformation. If so, find its kernel. All right. So here, every time you apply a vector in R3, what it does, it takes that vector and it crosses it with V sub 0. Well, V sub 0 is a vector. Well, let's see. A cross of those two. If I apply T on KU, well, that's going to be based on the formula KU crossed with V naught. But we know we could take K out and take U crossed with V naught. And that will be K T applied on U. So that works. And if I take T applied on U plus V, that is simply, let me just think, that's going to be U plus V crossed with V naught. Well, that's going to be U crossed with V naught plus V crossed with V naught, which is T of U plus T of V. So T is a linear transformation. And simply the kernel of T, well, if V equals 0, you're set. If V sub 0 equals 0, then the kernel of T would simply be all of R3. So whatever you choose in there will work. Otherwise, the kernel of T would be, okay, these are vectors. That will be the span of V sub 0. All linear combinations of that. Here we are. Number 6, we would like to look at M22 is right there, A, B, C, D, and it's going into R. So real, well, let's see. That's how the transformation apply. If I take the transformation applied on K, A, B, C, D, wouldn't you say that's going to be the transformation applied on KA, KB, KC, and KD? And based on this transformation, that's going to be 3 times Ka minus 4 times Kb plus kc minus kd. Well, can't I say that's k into 3a minus 4b plus c minus d, which is k applied on the transformation of a, b, c, d. It checks. And if I take t applied on a, b, c, d plus a, b, c, d, that would be t applied on a plus a prime, b plus b prime, c plus c prime, d plus d prime. That would be 3 into a plus a prime plus, no, plus minus 4 times b plus b prime plus c plus c prime and minus d plus d prime. But I could say that is 3a minus 4b plus c minus d plus 3a prime minus 4b prime plus c prime minus d prime, which is the transformation on a, b, c, d plus a prime, b prime, c prime, and d prime. So therefore it is a linear transformation. And if I apply the kernel of T, will consist of all matrices given A, B, C, D, which equal 3A minus 4B plus C minus D equal to 0. And that's a condition, and it's all good. If I look at this, so the transformation on matrix M22 is simply A squared plus B squared. If I take the transformation on K, that will be that equals which does not equal to K times T of A, B. Therefore, not a linear transformation. It equals K squared times that, not K. So that doesn't work. Now, let's play with this a bit. This is going to be kind of fun. Suppose T maps function from negative infinity to positive infinity into another function, negative infinity to positive infinity, no restrictions on those whatsoever. So T applied on f of x is 1 plus f of x. So if we take T applied on k f of x, that is 1 plus k f of x, right? That does not equal to k. For it to be, for this here is actually k into 1 plus f of x, which is k plus k f of x. And obviously that doesn't match because of that one. So therefore, not a linear transformation. How about this function? Well, here you're not affecting the outside. If you take t applied on k of f of x, that is k f of x plus 1, which is k times t of f of x. That checks. And if I apply t on f of x plus g of x, that would be f of x plus 1 plus g of x plus 1, which is t of f of x plus t of g of x. Therefore, it is a linear transformation. The kernel of t consists of the zero function. Okay, this is really nice. Let's do b first. So if I do b first, so we're going from p2 to p3. Okay, we're going from quadratic to cubic. That's not a problem. Be a linear transformation defined by this. Which of the following are in the kernel? Okay, if I apply t here on 0, according to this, that's x times 0, which is 0, right? There. If I apply the transformation on x squared, that would be x times x squared, which is x cubed, which doesn't equal 0. Therefore, x squared is not in the kernel of t. So it's fairly simple. You apply the transformation. If you get 0, it is in the kernel. If you don't get 0, it doesn't. So they're not saying for what values of x is this and that. They're saying, is it? Check. Or are they? Give you money. How about here? If I apply the transformation on 1 plus x, that will be x times that. That will be x plus x squared, which doesn't equal 0. So 1 plus x is not in the kernel of t. And of course, t applied on negative x is negative x times negative x. So it's always x times whatever that is. That is x squared, which does it could equal 0. They're saying, is it the kernel? If it is, it should automatically give it a 0. Therefore, negative x is not in the kernel of t. Let me fix this. Okay, let v be any space vector, any vector space, and let t be the transformation from v to v defined by, you apply the linear transformation on v, you get 3 times v. What is the kernel of v? Well, take 3v, set it equal to 0. That means v must be 0. Therefore, kernel of t is the 0 here. You're forcing it to be a 0 since it's not working out like that. What is the range? Well, think about it this way. You input the domain, the range, you get 3 times v. So for every vector, so we go v to w. the range of T is simply V. You input any multiple of that, say W times a third, and that turns out to be, alright, all of V. And really quick, almost done. Alright, nullity, pretty good. We take R7. Well, if we take R7, remember the dimension will be 7, right? Dimension of V will be the rank of T plus nullity of T. Where's that term? Right there. Well, in this case, dimension of V will be 7. The rank is what we're looking for, and nullity is 2. So that means the rank of T is 5. That's simple, nothing to it. Okay. And how about here? We're going with P3. Remember, P sub 0 is a constant, right? That's like A. P sub 1 is linear. That is AX plus B. So P sub 0 has 1, P sub 1 has 2, P sub 2 has 3. So here, if we're going for P3, we said the dimension of V, well in this case of P3, equal the rank of T plus nullity of T. Well, here the dimension is 4. Remember, 1 power more, because if you have a quadratic that has A, B, and C, quadratic is P sub 2, that has 3 of, the dimensions are 3 variables. The rank of T, I lost track where it was. And the nullity in this case happened to be a 1. So we know the rank of T will be 4 minus 1, which is 3. And continuing on. Now, if I tell you that the null space of T from the 5th degree polynomial is the 5th degree polynomial. So the null here, nullity of T is 6. We know that dimensions of V equals nullity of T plus the rank of T. Well, dimension of V is a 6. That is 6 plus rank of T. So the rank of T is 0. And we know that because it took the entire space. In general, if we're taking a polynomial, then we say dimensions of V would be the nullity of T plus the rank of T. Well, dimensions here will be n plus 1. Nullity is 3. So the rank of T would be n plus 1 minus 3. That's n minus 2. And that's pretty much it for this section.